Hello and welcome back. Let us try to understand the fourth and fifth assumptions of linear regression. The serial correlation or autocorrelation and multi-collinearity. So the serial correlation means the the correlation between consecutive errors or the error separated by some other number of period is known as serial correlation. In other words, if you have a correlation between consecutive errors, okay, let us try to understand what that means by consecutive errors. We built a model, there are x1 and x2 and so on xn input variables. There is y. Suppose that we built a model and we predicted some values and the errors are like this, right? 2, 4, 6, 8 and 10. For consecutive or separated by a range, I said that here the range is 1, right? Every record has got 2, right? If you want to calculate correlation, right, you need to take first day's error, second day's error, third day's error and fourth day's error, and you need to take the period, right? They are separated by some number of records. Is second day's error, only one record separation I am taking. Second day's error, third day's error, fourth day's error and fifth day's error. If you look at these two columns and try to calculate correlation, you will have one, right, strictly increasing. One is increasing strictly, other is also increasing. This kind of problem may happen in stock market kind of data, stock prediction kind of data, right? It is generally a time series problem and we should be using time series algorithms there rather than linear regression. If you have serial correlation or autocorrelation, that means the problem should be solved with time series algorithms. So there is a test called Durbin-Watson test, which ranges between 0 and 4. If the value is equal to 2, there is no autocorrelation. That is perfectly fine. That means a linear relationship is there, or the other relationship is there, but it is not a time series problem. If it is between 0 and 2, that implies positive autocorrelation is there. If it is between 2 and 4, and then a negative autocorrelation is there. So generally we can fix this by adding interaction terms or maybe removing the columns which are influencing the or creating the autocorrelation kind of behavior. So what is interaction term? If you have x1 and x2, two variables, and if you add a third variable by multiplying x1 and x2, the third variable is x1 into x2 into the dataset, that is called as interaction term. Generally that term determines the combined effect of these two features. X1 may affect in a particular way the target variable, x2 may affect a particular way in target variable, but when you combine these two and add third column, that may preserve or create a create an input variable which actually affects in a combination way, right? When there is a combined effect, it will actually create that. That's called as interaction effect. So general example is that if you are doing a radio ad and a paper ad to publicize your product, you want to identify how much effect is there in combination, right? If in combination with radio ad, paper ad, how much it is affecting. If you want to identify, you need to combine these two or multiply the numbers and add a new column in the data set and try to build a model. It will actually give you more accuracy. So generally autocorrelation problem can be solved by adding interaction terms into the data set. So that's about autocorrelation. And multi-collinearity. When you have more than two predictors or the input variables strongly correlated, that is called as multi-collinearity. Generally, multi-collinearity will not create any problem in making the prediction, but it is that we need to if you have too many columns which are strongly correlated, right, it will add lots of work to the processor, right, and the memory. So if you can reduce those features and build a model that actually gives you a quicker training time, or the model gets trained faster. Okay. And one more thing is that in some algorithms like linear regression, if you have two strongly correlated variables, like with one correlation, it will have a problem of dummy variable trap, which is nothing but when two strongly correlated variables are there and the algorithm is trying to do some matrix manipulation, it will not be able to find out the inverse. When you do some matrix manipulation, when you have two strongly correlated features, it generates a singular matrix. The singular matrices will not have the inverse of it, and it struggles to find the coefficients. So that's another problem with multicollinearity. Multicollinearity can be avoided by applying principal component analysis like algorithms. Okay, to check whether multicollinearity is there or not, you can actually do a heat map like this. For the data set, we have done a heat map. Here, if you see, the lines of code has got a strong relationship with the aggressive behavior score and activity score, right? So this data set has a multicollinearity. If you apply PCA, you can actually extract all the variance in the columns and create a small data set which actually saves lots of space and improves the training time, right? Okay, so we will see all that in the coming course. But multicollinearity is not really a danger to make predictions for many of the algorithms. For some algorithms, it will have dummy variable trap, but eliminating them is going to be good, right? Is good. Okay, so you can actually use a statistical test called variance inflation factor also. If the value is less than 4, no multicollinearity is there. If it is greater than 10, serious multicollinearity is there. In Python, I didn't find any method to do variance inflation factor, but in our language we have the methods to do that. So generally, we can use this correlation heat map and can understand whether multicollinearity is present or not. So dimensionality reduction techniques like PCA can solve the problem. Right, regularization is also another technique which actually tries to nullify the coefficients. Coefficients it makes 0 for the ones which are not important, or trying to have the same kind of effect on the target variable. So we'll see these techniques in coming classes. So these are all the assumptions of linear regression. Thank you.